Hello, and welcome to Construction Scheduling, the network schedule. A quick review before we begin. Our schedule will be based upon activities and their immediate preceding activity, or IPA. In Precedent construction schedules, activities are represented by objects, circles, squares, rectangles, or similar shapes depending on the activity. As an example, activities taking place on a weekend may be represented by a circle, while milestones are represented by some other shape. These activities are placed in the schedule in diagram form and read left to right. The nodes will have varying information in them. Most will have early start, early finish, late start, late finish. These items may be represented by dates or simply numbers which represent working days or calendar days. The lines in the diagram are not meaningless. They represent the links between activities. These lines represent the interdependency of one activity upon another. Links are also viewed left to right to indicate the relationship, meaning the left side of the line is the beginning of the link line, and the right side is the end of the line connecting the two activities. This also means that in this case, the link line represents a finish-to-start relationship between the activities. In other words, B cannot start until activity A is finished, activity C cannot begin until activity B is finished, and so on. The finish-to-start relationship is the relationship that most of us are familiar with. It is logical and therefore makes sense in the industry of construction. In a finish-to-start relationship, once an activity is finished, its succeeding activity can begin. By putting everything into a finish-to-start relationship, we can simplify computations and the schedule. But it is worth noting that computer software can quickly calculate any activity relationships. It is also worth noting that link lines between activities consume no resources, not even time, unless we want them to. As an example, in this typical finish-to-start relationship, the link lines consume no time. Our first activity is to place the concrete. The next activity is curing the concrete, which takes 28 days, and then the last activity is stripping the forms, which is going to take 2 days. However, since the activity of curing the concrete consumes no manual resources, only time, we may want to depict this same schedule as seen here, using the link line to indicate the delay between placing the concrete and stripping the forms. Once again, these are finish-to-start relationships. In other words, an activity cannot begin until its preceding activity has been finished. Let's now take a look at other activity relationships. Another type of activity relationship that may be encountered is the finish-to-finish relationship. In this relationship, two activities must be completed at the same time. Here, we see an example of the finish-to-finish activity relationship when setting a fence post, a simple task which requires the finish-to-finish relationship. As you can see, the second activity, setting the fence post, has a finish-to-start relationship with digging the hole for the first fence post. It is impossible to set the post until we dig the hole, but positioning the post is dependent upon setting the post. We can't position the fence post until it's placed in the hole. Now, if we want the fence post to remain plumb, we must backfill while keeping the post in position, finish to finish. Another activity relationship is the start-to-start relationship. Here, two activities must start at the same time. As an example, the placing of a concrete sidewalk. As the concrete is being placed, the finishers are screeding the concrete directly behind the placement. So, the placement of the concrete and the screeding must start at the same time. In the start-to-finish relationship, not to be confused with finish-to-start, an activity cannot be finished until a previous activity has been started. As an example, our concrete sidewalk may be delayed if we went to the traditional finish-to-start relationship. As seen here, it is suggesting that the concrete cannot be ordered until the form is complete. This is obviously not true. Ordering of the concrete is not dependent upon the completion of the formwork. And since most ready-mix producers want concrete ordered with some lead time, a better way to represent this would be as a start to finish with a delay. Since most ready-mix producers do require the concrete to be ordered in advance, an easy way to depict this would be as shown here. And what this schedule is showing is the forms have to be completed before the concrete can be placed. So setting the forms and placing the concrete is a finish-to-start relationship. Again, the forms have to be completed before the concrete can be placed, while the ordering of the concrete and the placing of the concrete is a start to finish with a 5-day delay. In other words, ordering the concrete must be done 5 days in advance of placing the concrete. As you can see, activity relationships are extremely important to the construction schedule. They can be confusing, but this is the importance of planning out the activities. Understanding the relationships between activities and defining activities are critical steps before beginning the construction schedule. Now, moving forward, for the purposes of this presentation, we will present everything in the finish-to-start relationship. Another extremely important aspect of proper scheduling is durations. A duration is the time it takes to complete a specific task. Once durations have been established, job calculations can begin. Job calculations are defined as ES, or early start, EF, or early finish, LS, late start, and LF, late finish. Once these items are calculated, we can calculate the total float, free float, and lag time is calculated later. The project calculations will assist the CM in finding the start times for all activities. It will also find the overall project duration, and it determines critical activities, which allows us to find the critical path. Critical path activities are those activities that must be completed on time or the entire project duration is impacted. Now here we see the calculations. The forward pass is the early start plus the duration equals the early finish of the activity. The backward pass would be the late finish minus the duration equals the late start of the activity. And finally, to check the total float, it is the late start minus the early start. The forward pass calculates the earliest times that any task can begin, while the backward pass calculates the latest time that any task can begin. From the forward pass and backward pass calculations, we can determine the float times, or time allowed to delay before any task must begin. After we complete the forward pass, the backward pass, and calculate our total float, we will calculate lag time and free float. Free float is the amount of time we have on an activity before it impacts the next activity. Lag time is the amount of time between two activities. Now, just a couple of general rules before we get started, since we have already talked about some of these items. First, never confuse link lines with activities. Link lines can have time associated with them, but they are not activities. Nodes can be almost any character, circles, squares, rectangles, etc. Once all the information is in, take the time to draw a rough precedent diagram. This will help you quickly identify if you have missed any activities. So now, let's go ahead and get started. This is an IPA table, or immediate preceding activity table. It outlines an activity and its immediate preceding activity or activities. As you can see, activity A has no preceding activity as it is the first activity. Activity B cannot begin until activity A is complete, and the same is true for activity C. And as you can see, the rest of the table is filled in. This is a good sketch to keep us on track if we begin to get lost in the activities. Now, let's move to the calculations for our schedule. Here is our sketched out schedule. As you can see, Activity B and Activity C cannot be completed until Activity A is completed. Activities D and E cannot be completed until Activity B is complete, and Activities F and G and H cannot be completed until Activity C is complete. Now this matches our IPA table. As you can see, the precedent for Activity B and C is Activity A, and so on. Now let's calculate the forward pass, and again, the forward pass is going to tell us the shortest amount of time in which the project can be completed. Now in the upper left-hand corner of the slide, you see a node which is similar to the nodes in the schedule. This node is the key. In the upper left-hand corner is going to be the early start, ES. In the lower left-hand corner is the early finish, EF. The top middle box of the node is the pre-established duration. Durations are established from experience and/or historical data. The upper right of the node is the late start, LS. The lower right is the late finish, LF. The middle left is free float, FF. And the middle right is the total float, TF. Finally, the large, rectangular box at the bottom of the node shows the resources required to complete the activity. To calculate the early finish of Activity A, we simply take the early start plus the duration equals the early finish, or in this case, 1 plus 1 equals 2. The early start of 1 for this activity only is a given, as Activity A obviously has no preceding activity. We can now calculate the early start times of Activities B and C. The early start time of Activity B and C is 2. This is coming from the early finish of Activity A. As you can see, the early start time of an activity is the early finish time of its preceding activity. Again, the only exception is the very first activity. We can now calculate the early finish times for both B and C, which are 6 and 4 respectively. And now we can calculate the early start and finish of activities D, E, F, G, and H. Activity D and Activity E are going to have early start times of 6, as this is the early finish of Activity B. Activities F, G, and H will all have early start times of 4. Again, the early finish time of its preceding activity, which is Activity C. And the early finish times of these activities are simply calculated by early start plus the duration equals the early finish. Now, the early start of Activity J is 7, the early finish of Activity D. But what should be the early start of Activity L? After all, it has 3 preceding activities, F, G, and H. When an activity has multiple preceding activities, the early start of the activity will be the latest early finish of its preceding activities. Therefore, in this instance, the early start of Activity L is 8, the early finish of Activity G. This only makes sense. If Activity L cannot begin until activities F, G, and H are complete, then obviously we will have to wait for Activity G to be complete before starting Activity L. We can now move forward to Activity K and M, completing our forward pass. And by completing the forward pass, we know that the earliest possible time to finish this project, again providing everything goes smoothly, is 17 days. At this point, we can also begin to calculate our late starts and late finishes by doing the backward pass. Late starts will tell us the latest an activity can begin and still finish on time, while the late finish tells us the latest an activity can finish without impacting the project schedule. We begin the backward pass with the last activity. To determine the late start and late finish of the last activity is quite simple. It is the early start and the early finish of the last activity. This only makes sense, because if each activity stays on schedule, or at least finishes before the late finish, then we should complete the project on time. We can now determine the late finish of activities K and L. The late finish for these activities will be the late start of activity M, K, and L's succeeding activity. So, the late finish for K and L is 16. To calculate the late start of K and L, we simply subtract the duration from the late finish. Therefore, the late start of K is 10 and the late start of L is 14. We can continue the backward pass. The late finish of J is 10, which is the late start of K. E is also a direct preceding activity of K. Therefore, its late finish is also 10. While activities F, G, and H will all have late finishes of 14, which is coming from their succeeding activity L. We can now calculate the late start for all of these activities, again, by simply subtracting the duration of the activity from the duration's late finish. We can now fill in the late finish of activity D, which is 8, and its late start is 7. And now we see a similar situation as when we were doing the forward pass. Activities B and C have more than one succeeding activity. Therefore, we have to determine which of the late starts will become the late finish for these activities. When facing this situation on the forward pass, we would always use the latest early finish. But here we use the smallest late start. Therefore, the late finish of activity B will be 6, which is coming from activity E, and the late finish on activity C is 10, coming from activity G. And we can now complete the backward pass by bringing back the late start of activity B to become the late finish of activity A, and this completes the backward pass. Again, the backward pass tells us the latest time an activity can start without impacting the schedule and the latest time that it can finish without impacting the schedule. And now we can calculate the total float. There are multiple ways to calculate the total float. We can calculate it by the late start minus the early start, the late finish minus the early finish, or the late finish minus the early start plus the duration of the activity. The system that one uses is usually convenience or the software being used. In any case, it is always best to use at least two of these formulas as a check on your calculations. Total float, not to be confused with free float, is the amount of time you have on an activity before it impacts the entire project. So let's start with activity M. The late start of 16 minus the early start of 16 equals 0, and the late finish 17 minus the early finish, also 17, equals 0. For activity L, the late start of 14 minus the early start of 8 equals 6, while the late finish of 16 minus the early finish of 10 also equals 6. We can now calculate the total float for all remaining activities. Now that the total float has been established, we can determine the critical path. The critical path shows the activities that must be completed on time for the overall project to be completed on time. These are considered the critical activities. In other words, if one of these activities is 1 day late, the project will be 1 day late. The critical path can be determined by following any activity that has a 0 total float. So, in this example, our critical path would be A, B, E, K, M. As you can see here, these are the activities with no total float. Lag is the amount of time between the early finish of an activity and the early start of a specific succeeding activity. It is calculated via the following equation. The lag between two activities is equal to the early start of an activity minus the early finish of a specific succeeding activity. Lag does not have a place in the activity nodes, but instead is listed along the link lines. Also, when calculating activity, we should do it from the last activity and move in a backward pass motion. Therefore, the lag between activity M and activity K is 0. We get this from the early start of activity M, 16, minus the early finish of activity K, also 16, while the lag between activity M and activity L would be 6. Now, even though we showed the zero lag previously, that was for informational purposes only. Normally, if there is no lag in between two activities, you will show nothing along the link lines. So, if we fill in the rest of our lag times, we should have 1 day lag between activities J and K, 1 day lag in between activities F and L, and 2 days lag in between activities H and L. In this schedule, we have no other lag in between activities. You can imagine the importance of lag when the schedule begins to get detracted by unforeseen conditions. Lag is also critical when it comes to crashing the schedule, but let's save that for another segment. And finally, free float. Free float is the amount of additional time you have on an activity before it impacts the next activity. Free float is equal to the smallest lag value of all links returning to an activity. As an example, the free float of activity L would be 6, while the free float of activity K would be 0. And when we complete all of the free float, the completed schedule should look like this. Now, this is a fairly simple schedule, so the amount of free float is not particularly puzzling. But you can imagine a large schedule where an activity may have multiple link lines returning to the activity with different lag times on each link line. The free float could quickly become an important resource. And speaking of resources, the one thing that is missing in the schedule is reality. Because the reality is when we did this schedule, we did not consider resources. We assumed that we had all the necessary resources to complete each task. In our next segment, Resource Allocation, we will use this schedule to deal with a sudden loss of resources. But for now, let's review our steps to completing the schedule. Listed here are the sequential steps of the schedule we just completed. 1. Assign 1 as the early start date of the first activity. 2. Calculated the early finish time of the first activity. 3. Early start of activities are the early finish of the preceding activities. 4. Repeat steps 2 and 3 until the early start and early finish of all activities have been determined. 5. Assign late start and late finish to the last activity. Late start equals early start, late finish equals early finish for the last activity only. 6. Calculate the late start and late finish for each activity. 7. Calculate the total float. 8. Determine the critical path. 9. Determine lag. And finally, 10. Determine free float. And this concludes Part 2 of Construction Scheduling, the network schedule.